Advertising on YouTube helps me reach engaged customers.
Sorry about that. Don't know what happened. I think it's still on live on YouTube, so that's good. Okay, so let me get started. So I'll try to get on this computer as well. Yeah, so in the last class, we saw, lattices, definitions of lattices, monotone functions on lattices, and we had a definition of fixed points, and we had saw a characterization of fixed points of monotone functions over complete lattices. Characterized in terms of this Tarski's theorem, which really identify two kinds of set of elements on the lattices. One was a reductive set, RED, which contains all elements that are on all descending chains in the lattice, and then the theorem it characterized the least fixed point of a monotone function on that lattice as the greatest lower bound of all elements, a greatest lower bound of the set of all elements that are in that reductive set, okay, which is defined as things that appear on descending chains. That is, f of x is less than or equal to x. Similarly, the greatest fixed point of any monotone function was characterized as the least upper bound of another set of elements in the lattice called the extensive set, which contains all elements that appear on all ascending chains in the lattice. Okay, so that's how it was characterized, and we saw some examples there. So what Tarski's theorem, or its way of characterizing least and greatest fixed points, say is captured by this picture, and I want to start today's lecture by explaining that. Okay, just this thing of these dotted things, just ignore. It's not relevant. We will get to that later on. So this subset here, I hope you can see my cursor that I'm pointing out. So that is the reductive set. Okay, that's the reductive set. Okay, so that's why it says elements in that reductive set are those for which f of s is less than or equal to s. And what Tarski's the first version of the theorem says is that the greatest lower bound of that set is actually the least fixed point of function. And then the other set here is the set of elements on the extensive set. Okay, that is elements on ascending chains. Now, this intersection of these two things are they characterize those elements which are the fixed points, okay, for which fs is equal to s, and so all the fixed points of f reside in that sliver that denotes the intersection of these two sets. So what Tarski's theorem additionally says is that the greatest lower bound of the reductive set is the precise, exactly the least fixed point of f, and and the least upper bound of the set of all elements that appear on ascending chains is the greatest fixed point of F, okay? Of monotone function that describes these two sets. Okay? And we saw some examples. I'm not going to go through the examples again. So, are there any questions on doubts about the statement of Tarski's characterization of fixed points at this time? Okay. So if not, then I will get to a simple sketch of a proof of Tarski's theorem. It's fairly simple and it's interesting. Okay, so this is the first version of it. You can it says that the least fixed point is the greatest lower bound of the reductive set. Okay, so in order to prove this, that the least that the greatest lower bound of the reductive set, it is indeed the least fixed point. That is what I'm going to show you in this in this proof. Okay, so so as you know, so this least fixed point is the least among all fixed points. Okay, and that's how least fixed point of F is defined. But here, Tarski's claim is that can be characterized as the greatest lower bound of the reductive set. So the proof itself is broken down into two parts. First is to show that indeed the least fixed point of F is indeed the reductive set includes, or it contains, the least fixed point. And the least fixed point is indeed reductive. And then the second part shows that the greatest lower bound of that is indeed, the greatest lower bound is indeed the fixed point. Okay, so the real doubt here is that, of course, it says that this is the reductive set is well and good. But what is to say that the greatest lower bound of this set here is indeed fixed point? Because the greatest lower bound of any set in a lattice doesn't have to be contained in the set itself, so it can be outside also. So that's why this is also important to show that indeed the greatest lower bound is the fixed point. Okay, the first part of the theorem is fairly easy to show, because if F is a fixed point, that means that F applied to the least fixed point is equal to so because the least fixed point F applied to that must be equal to F its that least fixed point itself. So but that means that it has to be F applied to LFP of F has to be less than or equal to LFP of F for it to be equal. Actually, the fixed point is an element for which F applied to that is equal to the element itself. That, of course, implies that F applied to the fixed point has to be less than or equal to. And since this set is reductive, this is exactly the condition that needs to be satisfied for any element to be part of the reductive set. And therefore, LFP, the least fixed point of F, is certainly belongs to the reductive set. Okay, so that is simple enough. Okay, so any questions there?
So we also have to show that LFP is indeed a fixed point, right?
Yeah, that's the second part of the thing, which is shown as a lemma that in the that follows. Yeah.
So you're saying that this equality is follows from the thing that we are about to
Good
prove.
one. So the yeah, I mean, the least fixed point is there in thing, and we will show that this indeed is a fixed point. That's the second part. Okay, that the greatest lower bound is the is the fixed point. Yeah,
Yeah.
is the
Hmm.
fixed point as well.
Hmm.
Okay, and so when if you want to show anything, and as any element is a fixed point of a function, of course you will have to show that if x is a fixed point of f, you have to show that f of x is less than or equal to x, as well as x is less than or equal to x. So if both of them are true, then it implies that fx is equal to x, and that's what is shown. So the first part of the proof here is the A. It shows that f applied to the greatest lower bound of the reductive set is indeed less than or equal to the greatest lower bound. Okay, so that's what this part, the above thing A is showing. So what since what the greatest lower bound of the set of all elements in the reductive set is, I mean, it's a lower bound. Therefore, the greatest lower bound has to be less than or equal to x for every element x in the reductive set. Okay, correct. Okay, so that since this is a lower bound, so that should be true for every x in that set. So since f is monotonic, and so f applied to the greatest lower bound is indeed less than or equal to f of x. Okay, and which itself is less than or equal to x for every x belonging to the reductive set, which means that f applied to this greatest lower bound of red f itself is a lower bound. But of course, this but this has to be less than or equal to the greatest lower bound, obviously, right? So we have shown here that f of red of f is indeed is a lower bound. Okay, is a lower bound for every elements inside in the reductive f, and which means, but that has to be less than or equal to the greatest lower bound. Okay, which is what you get from here. So f of this thing, yeah. So because that itself, this is a lower bound, and this is the so it has to be less than or equal to the greatest lower bound, and therefore, so which really means that this itself is f applied to this the greatest lower bound is also inside the reductive set. Okay, so that completes the proof of the first part of the thing. Now, in the second part, we have to show that the greatest lower bound is less than or equal to f applied to that element. Okay. Now, since we've already shown that f of applied to greatest lower bound is less than or equal to the greatest bound, which means that, and therefore from A, and since the monotonicity property of f together imply that f applied to this has to be less than or equal to f applied to the right hand side. Okay, therefore f applied to red f itself is part of the reductive set. Okay, because f applied to this is less than or equal to f applied to something, and therefore and therefore the because if that is part of the reductive set, then the greatest lower bound has to be less than or equal to f of applied to the greatest lower bound. Therefore, and that shows that so both inequalities hold within. Therefore, this the greatest lower bound is indeed a fixed point. Okay, so that's and so that's how the proof goes. And you can have an analogous proof of to show that the greatest fixed point is the least upper bound of the extent. Okay. So any questions?
I still don't understand like how this implies that LFP is equal to the greatest lower bound of red of f. Can you please repeat that?
The LFP?
Yeah, LFP of. Can you go back to the previous slide? Yes. So, what we have shown, how does that imply that LFP of f is equal to the greatest fixed point? I mean, the greatest lower bound of red of f.
So the greatest lower bound is indeed a fixed point. And the yeah, so and since but this it's a fixed point, and it indeed belongs to the it indeed belongs to it is inside that set. Okay, it is a fixed point. So what is the least fixed point? It is something that it is a fixed point, and it has to be the least of all the things in that set. Okay. See, the least fixed point is indeed reductive, and therefore it has to be in that set. And this greatest lower bound is also a fixed point. Okay. And that is actually the greatest of all of all the lower bounds, and that indeed it is inside that, and it is the greatest lower bound of that set, and that means that it has to be the least fixed point. Correct?
Yeah.
Because it is already in that set, and if that is the least of all that element in that set, and so that is already there in that set, and so it's also a fixed point, and by definition this one is the least element. Okay. And that's those two together will guarantee that this is the least, least among all the fixed points. Yeah. Okay. So how do we apply? So all this, fixed point theory, predates to, showing, I mean, inductive, the programming logic and the inductive invariance and so on. So how exactly is this applied to in the context of reachability, analyzing software, reachability properties of software? And that's where what fixed points means to what kind of functions as it relates to transition system becomes relevant. So recall, a transition system has three components: a domain of the universe of the set of all states, okay, and then an initial a predicate that defines the set of initial states, and a binary relation that captures the the transition, the successor state relation. Okay? And in order to, and we will see how the set of all reachable states, that's what I mean when I say reachability, can be characterized as the least fixed point of a suitably defined function over this partially ordered set. Okay, the lattice, the complete lattice, which contains, whose elements are the subsets, whose domain is the power set, that is, whose elements are the subset of over the universal, the set of all states, and the set inclusion. Okay, in the lattice, we have already seen that example earlier. So, so that the set of all reachable states can be defined as a function over this lattice that maps set of states to set of states. Okay, and that's what we are defining here. Okay, we've already seen through a couple of examples on your problem statement. So I'm going to be reiterating that thing. So that is defined. First, we define the a post, which is actually the image function that you saw on your problem set, okay? Which computes, given a set X, it computes the image, that is the set of all, the image of X under the transition relation R. Okay? In the problem set example, we have used T instead of R. So post is exactly IMP applied to X. Okay? And so the set of states that are reachable from the initial set can be now described as, so as I said, this is given any S prime, it's, so it is, it says that, so it is S, it's something that maps, okay, it's the set of all states that in one step, set of all states that in one step, set of all states in one step, lead to a set of all states that you can get to from states inside X in one step of application of that relation. So that, as you saw in the thing, we had defined it as an existential quantification, and using existential quantification in set theoretic notation, this is how it can be represented. Therefore, the set of states that you can reach in up to k steps of R can then be defined as post applied to k number of times, starting with I. Okay? Now, if you define a collecting, a function which kind of collects, starting from the initial state, all states that are reachable up, reachable in one or more steps of applying to R. Okay, that's what this F here denotes. Okay, is denotes, which is defined as I. Okay, I applied to post of post of X. Okay, this is it. Just I'm sorry, this F itself is not that. Okay, F of X is just takes the union of I and with the image applied to X. Okay, then now which was IM of X. Now X can then be, this will be the least, fixed point of, then the set of all reachable states will be the least fixed point of such a function. Okay, when you can apply, when you can kind of jumpstart it as as shown here. So we start with the empty set, okay, and S naught is the empty set. F1 will be F applied to S naught, okay. So that is I union post of S, and that's the initial state. And then now you could apply F to itself, and once more, and that way you can keep on doing it until you get to F of Si itself is contained in Si. Okay, then that thing is a point where you have reached a fixed point. And therefore, the set of all reachable states, that is, states that can be reached in zero or more states, where zero iteration is considered as the initial, we define it as the initial state, can be defined as, characterized as the fixed point of such a higher order function. So it is, so that's why the fixed point theory is relevant to being, for analyzing and computing the set of all reachable states of a transition system. Okay? So now, so we could see that the least fixed point. So, and you can see why, we started with this whole process, where starting with how to prove loops, correct? So because the we saw whole logic was was easily automatable, for straight line and branching programs. Okay, it was only when you got to loops that you had to discover inductive invariance, and then we saw that one of the strongest inductive invariant is exactly the set of reachable states of a transition equation as it applies to loop. If the loop body is captured by the application, I mean, if the loop body application of one iteration of the loop body can be captured by a transition relation, then the set of all states that you can reach by executing the loop zero or more times can be characterized as the fixed point of this collecting higher order function that I have just now defined. So that's the relationship to the thing. And the least of these, there could be several fixed points of that higher order function, and that each of them will represent one inductive invariant for the loop. The least among them will characterize exactly the set of states that are reachable in all iterations of the loop, and so that's why this theory of fixed points will be relevant. There. So similarly, you can set this computation of least fixed point. Getting the fixed points also using descending chains by removing, but we'll get to that in a moment. So that's what I'm saying. So what Tarski's theorem characterized. So this is okay. So why I'm showing this? This one, see, Tarski's theorem was a set theoretic characterization of all fixed points of monotonic functions, but it did not give a computational flavor. You had to consider all descending chains and ascending chains in the lattice. So effectively, you have to look at all the entire lattice, whereas this intuition that I just now showed here gives you a kind of a specific directed way to compute the least fixed point, and that's what is shown here. So if you apply that, collecting what I call as collecting higher order function, okay, which in the problem set I defined as capital IM, then what this method that I just showed says is that by repeatedly applying that that function, the higher order function, starting from bottom until you reach a point where you cannot be adding anymore, that will be the least fixed point. Okay, so this is a way of computing it through repeated applications of self-application of a higher order function starting from the empty set. Okay. Similarly, you can have a characterization which starting from top, the set of all states, and defining a monotonic function G, which kind of removes states from it until you reach the greatest fixed point. And that is the difference here. So what this illustration shows is that there is a way to compute these fixed points that reside in the sliver here through iterative application of a suitably defined higher order collecting function or reducing function. So you hear by this method, I say this is there's a computational flavor because you don't have to look of all the elements in the lattice. You can just start from bottom and then keep iterating over this collecting function until you can't be adding any more functions, and that is exactly would be the least fixed point. Okay, so that's what this thing says, and so how would you then compute? Okay, you've seen this higher order function that I just now defined. Okay, in which and by applying that function repeatedly, starting from bottom, you show that you will reach the least fixed point. How about reaching other? So that is the strongest inductive invariant, okay, for a loop. Because when I say inductive invariant for a loop, then you have to assume that, okay, what I'm really referring to is the by using the transition function corresponding to the body of the loop. Okay, all the other inductive invariants that you have here will be. I mean, all the other fixed points that you have here will be representing the other inductive invariants. Okay, so when F is defined as what I showed here, earlier, so it is pretty much what it does is here, all I've shown it here, true itself is a fixed point of such a collecting function, correct? And therefore, your the GF P, the greatest fixed point, will actually, this point will move to T, okay? For that collecting function. So my question is, while you could get the least fixed point by iterating starting from bottom, how would you get to other fixed points that are weaker than this? Okay, so or other inductive invariants. Can anyone guess? Okay, so I've shown one way just now through by iteration to do this. How can I modify that function, that higher order function, so that I'll get to something which is a weaker inductive invariant. Okay, so that's the question I'm raising. Okay, so remember that here this function was defined starting with I as the starting by bootstrapping from I. If I choose anything which is a superset of I, which contains I, okay, and then I do the same thing, okay? Or in other words, if I start, instead of starting with bottom false, if I start with any other set that includes, okay, that is another way to view, or you can view as if I make F2 be not with starting with I here, something which is a superset of I will then lead to something which is which leads to a fixed point, which corresponds to something which is weaker than, it will be a weaker inductive invariant. Okay, so what I'm saying is you can use the same method to compute other inductive invariants that reside here by as fixed points of collective functions that start with supersets of I. Okay, so, or in other words, you can, instead of starting with bottom, if you start with something which starting with an element and then you follow this chain, starting from a set which includes the initial, which is a superset of the initial state, then you will get another chain which will end up with a fixed point which is weaker than the least fixed point, but some other element inside this, okay, and so on. Okay, so for example, if you start with the set of all states, which is top, then using that collective function, top itself is a fixed point. Okay, therefore, in one step you will reach the fixed point. Okay, so as you can see, so this is one way to get to use this iterative application of this higher order, collecting higher order function. As you can see, this collecting higher order function is indeed obviously monotonic, right? Why? Why the collecting function is monotonic? Can anybody? The way collecting function is defined, why is it necessarily monotonic? And that's why this iterative application will indeed end, because it is monotonic, because it is adding at each step, it is adding something to what already exists, which is the image, and that's why it is guaranteed to have a fixed point. And you can consider this iterative method as one way to compute it in a directed way, without actually looking at the set of all descending and ascending chains. Okay. Yeah. So, and that's what is now characterized this method of computing and iteratively by iterative application of higher order monotonic higher order function on the lattice was actually due to Kleene, and it is stated as Kleene's fixed point theorem, and that as it applies to computing inductive invariants. Okay, and that's what we will I will state next. Okay, so any questions about the arguments this illustration that I made about iterative application of this higher order function? which I will now formalize in Kleene theorem. Any questions here?
No, sir.
So we will define, so as ascending and descending chain. These are totally ordered ascending and descending chains. Okay, it's a sequence of elements that are strictly, less than or equal to. Okay, and the height of the lattice is defined as the length of its longest chain. So when the function is, the collecting function is defined as I had illustrated, that is, it can characterize the set of k, a set of states that are reachable in k steps. Okay, in order to ensure that this method of computing, okay, if this way of computing by iterative application of this thing, iterative application of higher order function requires an additional constraint, okay, of computing strictly ascending or strictly descending chain that start from either bottom or top. Okay, so that will require an additional constraint for that, for it to guarantee that when you stop adding any more elements to that iterative computation, that what you get is indeed the least fixed point. Is it requires that function, in addition to being monotonic, to also be continuous. Okay, continuous function. A monotonic function is said to be continuous if for every so it is either join continuous or mate continuous. So for join continuous, the definition is for every ascending chain in C, ascending chain C in the lattice, the ascending chain that you get by applying F. Okay, no, I'm sorry. So for every ascending chain in that in a lattice, and suppose we have two lattices X and Y, and F is a function that maps X to Y. Okay, and then a function F, that maps lattice partial orders from one partial ordering set to the other is said to be continuous if it preserves the upper bounds of all ascending chains. That is, if for every ascending chain in X, okay, and you apply F to every element in that ascending chain, then the upper bound of that, since F is monotonic, that has to be an ascending chain as well. F applied to every element in that chain, ascending chain, has to be an ascending chain in the lattice Y. Okay, so what this function being continuous requires is that the upper bound of the ascending chain that you get by applying F to every element in C should be the upper F applied to the upper bound of C of that ascending chain in X. Okay, so it's in that sense it is F is said to be continuous if it preserves the upper bounds in both those sets. And this neat continuity is defined analogously. Okay, so what this actually means pictorially is illustrated here. Okay, and suppose that you have a domain, a partially ordered set X here, then you have an ascending chain C appear like that, F is said to be continuous if the upper bound of the chain in Y, in the domain Y, okay, that's what this thing is, which you get as a result of applying F to every element here, is exactly the result of applying F to the limit of this, this upper bound of this chain. Now, when you extend this to infinite chains, then, so continuity is, guarantees that limits of ascending chains and analogously descending chains are preserved. Okay, so and that is an additional. That's what continuous the continuity assumption says. Then,
Sir, I have a question here.
yeah, yes.
So in the definition of continuous functions, say f, nowhere have we used the fact that f is monotonic, right? So, I mean, why is it monotonic? Why is monotonicity?
But then otherwise, F applied to that will not be an ascending chain on Y. No?
But that's fine, right? All we need is that the f and the disjoint union must, or rather the join must commute with each other. So F doesn't have to be.
Yeah. I think I'm yes. You're right. That what you're saying is if this thing applies to you can have whether, but then that the limit you may not be able to compute as the ascending chain. I mean, I think I'm so your point is that this continuity can be defined for non-monotonic function as well.
Yeah,
that is true. But I think that we will be using this specifically in our case where X and Y will be the same domain. Okay, and therefore this will be we will take into in which case it will be ascending chains. Okay.
Okay, so we want the image of an ascending chain to be an ascending chain in our case.
Yes, in our case. Yes.
Okay, thanks.
So, and that's what this thing is saying. Okay, so this has to be true for every. See, for if they're ascending chains, then the upper bound of So the upper bound of that is so that's what. So if it has ascending chain, then the limit of that means that you can extend that to infinite chains as well. Okay, so the and that's why if you use the Kleene method of iterative application of a monotonic function, in addition to that being you need the continuity assumption as well. Okay, because it has to be then you're not guaranteed to reach if it's not limit preserving, if you then you will have to then there's no guarantee that you can get to the least fixed point by just considering one ascending chain that starts from from bottom. Okay, so that's why you see Tarski's characterization looked at all ascending chains over the lattice, whereas here this iterative method is called Kleene's iteration. It looks at one particular chain starting from bottom. Okay. Now, as you probably already, some of you might have guessed, if our domain is finite, the monotonicity of the function itself guarantees continuity. Okay, continuity because if it is monotonic, then it and limit preserving. Because eventually the limit. After finite number of steps, the upper bound itself will be the limit of that of that chain. But for infinite systems, then you need this continuity assumption as an additional requirement in order to ensure that it is enough for you to consider one particular ascending chain starting from a bottom, in which the function f is applied repeatedly. And that's what is captured by Kleene's fixed point theorem. Okay? So it says if S is a complete lattice and F is semi-continuous, F is continuous if the join continuous. If it is continuous for both join and meet, for both ascending and descending chains. I mean, for join and meet, then it will be considered a continuous function. So then, if it is continuous, then the least fixed point is the limit, which is the least upper bound of this ascending Kleene chain. Okay, and the greatest fixed point of a function that generates a descending of a function, of a monotonic function that can be computed as the greatest lower bound of a descending chain. And this, I mean, I'm not going to show you a proof, but it can be shown by, I hope it's intuitively clear, because once you have this limit, continuity guarantees limit preservation, then this can be extended to infinite chains as well. But you can prove this using property. You will need both monotonicity and continuity, that the fact that upper bounds of chains are preserved. Using that, you can prove this by induction on the number of iteration, Kleene iteration, on induction on K, the number of iteration it takes. So I will leave that as an exercise, and you can actually find that proof on in the text that I have given you, as well as on Wikipedia and so on. What I want to illustrate now is how.
Sir, can you go to the previous slide? What is G?
Okay. That is something that, see, when you consider, G is another higher order function, okay, that generates, where you will have to, in order to compute it as a greatest fixed point, just like we defined a collecting function, okay, higher order function, you might have to define a function that removes things, okay, from your starting set, okay.
Yeah.
And that is so. The greatest fixed point can then be computed by as a descending chain generated by a suitably defined higher order collecting function, and that collecting function will have to be suitably defined so that it generates, it removes things, okay, and then generates a descending, so that you can perform a descending Kleene iteration. Okay, so I think the next slide, okay, will tell you, and I'm going to give that also as kind of an exercise for you to see what that G is. Okay, So be patient for a moment. Now, here is a picture which kind of gives you an idea of how to compute all inductive invariance, say for a loop. Okay. So as I've already said, whenever I say inductive invariance for a loop, I mean, when I say loop, I assume that the loop body is captured as a transition relation. Okay? And then once it is captured as a transition relation, which captures the effect of executing the body of the loop for an arbitrary, from an arbitrary state, assuming you enter the loop, then you can define the inductive invariance for that loop by defining a collecting function that generates an ascending chain. Okay. Now I've told you, I've asked you to believe me that you can also define an appropriate function g, which generates a descending function as well, and then in that case you can compute that as greatest fixed points. Okay, so this picture kind of illustrates all the how you could potentially compute different inductive invariance for a loop. What you saw just now in the collecting function that I showed you, and that you already are working on in the problem set, was computing it as the least fixed point of an ascending chain. So then you start with an initial set of states, defined by an initial predicate, and then you perform cleaning iteration starting from empty set, in which you've used the initial predicate embedded inside as the starting state for inside that collecting function. And then when you reach the fixed, when you reach the limit of that cleaning iteration, what you get is the least fixed point, least inductive invariant. That is the strongest inductive invariant. Okay. And once you once you have that, then you can prove potentially any property by just showing that that implies the property P here is any given property. Okay, so that is the strongest inductive invariant. That's also the strongest post condition for the loop as a whole. Okay. This is the strongest inductive invariant because it's inductive because it's a fixed point. It's an invariant because it contains the initial state, because you started with this entire cleaning iteration with the initial state. Okay, that's why it is it is an inductive invariant, and that is the strongest post condition of the loop entirely. Okay, because it contains the set of all reachable states that you can get to by executing the loop 0 or more times until it terminates. Okay, so but they can be, as we have seen in our examples for loops, that there can be other weaker inductive invariants. So every predicate that I've shown here that has a hat on top of it, I'm assuming it's inductive or it's a fixed point. Okay, and as you can see, since they all contain the initial predicate, they are all P1, P2, P1 hat, P2 hat. They're all inductive invariants, weaker than the strongest one, which I've denoted as PS, PS hat. Okay? Now, you can also compare, and of course, T, the entire set of all states itself is an inductive, is vacuously an inductive invariant. That's why I also have a cap on that. okay, as I've already told you, is so each of these things, these weaker versions can also be computed as Kleene iteration, as I have already observed, by choosing a collecting higher order function that is a superset of init. Now the question is, so the real verification question is, you usually start with a property, okay, and then you have to see what is the what is an adequate inductive, strong enough inductive invariant that I can use to prove that property. So that is the real challenging problem. Of course, if P itself, the property itself, is inductive, then your job is easier, is trivial. Okay. If not, then it is then that you have to look at what inductive, you have to search for an inductive invariant, or you come up with an inductive invariant. What Kleene iteration, which is the basis for all model checking methods, does is it computes the strongest inductive invariant. That is one way to ensure that you can prove any property, okay? Because you can then, by computing it, you can show that you check if that strongest invariant that you compute implies your property, okay? But you don't know ahead of time, okay? I mean, of course, if you're successful in doing it, nothing like it, okay? But firstly, as you can see, the Kleene iteration is not the most, it is not the efficient way to do it, because this, the height to which you need to iterate might be large, okay? And therefore, it is always useful to do, have other ways of, computing this inductive invariance. This greatest arriving at, because you have to guess, okay? You cannot, in order to get to something like P1 hat, you have to guess what superset of init that I can actually start from in order to get to that P1 hat. As you can see, P1, I've written this P1 hat and P2 hat as everything contained in P. So that's why they are all strong enough to prove the property P, which I'm assuming to be not inductive in this case. That's why you're starting searching for that. Therefore, when it is, so the other method, of course, could be that maybe you can start from P, okay, then compute the greatest fixed point of a descending chain generated by an appropriately defined a container function that removes elements, okay, and then you can arrive at this, something which is inductive, which like PW hat, okay, which is kind of the weakest inductive invariant. That is the greatest fixed point. What you compute as the greatest fixed point will be the weakest inductive invariant that is strong enough to prove your property P. And maybe that the number of iterations that you will have to do in order to descend, compute the greatest fixed point of the descending chain might be more efficient. Okay? Therefore, you can also have methods, that I call as backward methods or descending the chains to compute this weakest. Weakest among the thing, and that is also quite possible. Okay? And it's very much used. Okay, so the real exercise is what is a suitable predicate transformer function G that can be used to compute inductive invariance as a greatest fixed point, which can then be used to compute P weakest. But that once again will still have to use Kleene iteration. Okay, so there are model checking tools. Actually, model checking tools is either usually the earliest model checking tools all computed inductive invariance either using this using Kleene iteration over ascending chains, or Kleene iteration starting from the property computing on a descending chain. Okay, but more recent and more advanced ones use other idea. Why should, okay, you can always do this. Okay, that is a very good directed way of doing it, because the forward method is the strongest inductive invariant method, is very directed, because you know, if I can always start from the initial predicate. The backward method, I know that I can always start from the property that I want to check, okay, and then compute the weakest, weakest inductive invariant. If both of them use iterative, iterative methods which may not scale up, and therefore that's why it is also relevant to consider other things, okay, which are in between in strength between the weakest and the strongest ones, such as P1 hat and P2 hat. Why? Why, you may ask, why is it, how can you get to that? Okay, of course, though, those methods may not completely use cleaning iterations starting from bottom or top, but rather they use methods where you kind of guess an approximate inductive, a potential inductive invariant that may not exactly be inductive, but close enough to an inductive, close to an inductive invariant. Then you may be able to use methods to converge on these things. Like, for example, if you could somehow get, of course, if you could guess P1, say a non-inductive set like P1, a predicate P1, which still implies P, but it's not inductive, okay, but it is close to being inductive, then maybe you could start your backward method and then get to P1 hat in a quicker, and you can achieve quicker convergence. Okay, so those are the more recent methods, which are called inductive model checking, where you have some way of either getting to other inductive invariants, which are strong enough to prove your property, whose convergence depth is. And how do you do that? We will look later in this course a couple of methods. What is interesting is this method now, this general, but one thing you have to observe is all of them are doing a searching, different clever methods for searching for inductive invariants. Okay, eventually they'll have to eventually look a good way of clever ways of converging on one of these inductive invariants that safe to prove P. Now, so I'm already gone beyond the thing. So maybe I'll only state one thing here to say that I said that maybe you can guess approximate invariants, that are close to being inductive but not inductive enough, and then you can use these, still the notion of cleaning iterations and so on to get them to be inductive. So, and those ideas are now used. The way to guess approximate inductive invariants, they use machine learning techniques and so on. So, combining machine learning techniques and these traditional logic-based model checking methods to converge on inductive invariants to get to safe inductive invariants faster for the thing. Okay, so and that is the reason that I for spending. I think it's very important for you to understand the theory, and I hope you appreciate that. So because after all, at the crux of it, all these inductive computing inductive invariance methods are actually doing search of inductive invariance over this lattice of the fixed points of these collecting functions. Okay, so I'll stop there. So take any questions. Yeah, so some of these things are discussed in this reference. Okay, and so yeah, even if you cannot think of questions now, please review the lecture and come up with questions that you might have. Yeah, so think about this problem, how you can define this generate a weakest inductive invariant for that is contained in a property by defining an appropriate G that computes it as the greatest fixed point of a descending chain. I will show that to you in future class. Now, the only thing that I want to mention is from starting from the next class, we will see how this fixed point search, why this fixed point theory is relevant for abstract interpretation or static analysis, where the idea is here what we're doing is we are computing precise inductive invariance because the domain that we are using is exactly this the set of states. We are not, so that's in that sense these are called precise inductive invariance because they are predicates over real states. But there's also a notion that you can approximate these values, okay, the state values, and then you can actually, instead of computing inductive invariance on these precise domains, you can compute them over approximate domains, okay, that have some relationship, what are called abstract domains, okay, and that's what static analysis does. And there you get a big benefit in terms of efficiency of doing this Kleene iteration. Okay, if you are willing to approximate these domains, and that's what static analysis is, abstract interpretation is, and so in the next class I'll define certain notions that are needed to establish the foundation for static analysis. Okay. Sorry for running over, saving the time, and I appreciate your patience. Yeah. Thank you.
Thank you.